Welcome to Minikun's Health Tutorials. Today we're going to look at the statistical hypothesis testing procedure. So basically, a statistical hypothesis testing procedure starts by the observation of a possible difference. In clinical research, for example, we might have observed in the actual population or we might have formulated hypothesis presuming that in the actual population, treatment A might be doing better than treatment B. So we presume, in other words, we suspect a possible difference in the population. So, and this difference is actually our research question. So we go ahead to conduct a study, and then we do statistical hypothesis testing to prove whether this difference really exists in the actual population. In some cases, this difference might not be between two or more populations, but we may try to compare a sample value to a population value. So that's to say, inferential statistics basically comes in two folds. Either we are comparing a sample value to a population value, or we are comparing two or more population values. As I gave the example, for instance, we are comparing the efficacy of treatment A in the actual population to the efficacy of treatment B in the actual population. So we might presume that, okay, maybe treatment A is our new drug, and we are comparing its efficacy to the standard treatment, which might be, or even a placebo. So after observing this difference, we go ahead to formulate hypotheses in support and in support and against our research question, which was that there is a difference. So basically, our research question is what we call the alternative hypothesis. That's what we actually intend to prove. To say, for instance, sorry, let me use the pointer. To say, for instance, treatment A is more efficient than treatment B. This is actually our research question. In other words, this is actually the first stage of the hypothesis testing procedure. But due to sampling error, in other words, for the fact that we never conducted our study on the actual population, for instance, mu A represents, for example, depending on our judgment criteria or criterion, probably we said we were going to measure maybe the mean hours of sleep after taking, let's say, hypnotic A, and the mean hours of sleep after taking the standard treatment, which is hypnotic B. So based on our judgment criterion, we are trying to say, okay, the average mean hours of sleep after taking the standard the new treatment or the new drug would be greater than that of the average hours of sleep after taking the standard treatment, or in some cases a placebo. So this typically a superiority hypothesis test, or if we move out of clinical trials, of biostatistics to clinical trials, then I would say this is a superiority clinical trial. That's just to tell you that the hypotheses are actually formulated to suit our interest. In other words, to suit our research question, the difference that we're actually trying to prove. In other words, we could have said maybe the new drug is not worse than the existing drug, or we could have even said the new drug is worse than. In statistics, you would get to understand why. In statistics, like normal statistics, statisticians are actually interested in criticizing. So they could say, okay, the new drug is worse than the treatment, like the existing, or in other words, the standard treatment. But for the pharmaceutical laboratory, he formulated the hypothesis to suit his interest. Why would I waste my time fabricating a new drug just to prove that the new drug is worse than the existing drug. So I'll definitely formulate the hypothesis in support of what I'm doing, and I'll make sure I produce a drug that would meet what should I say, that would prove the alternative hypothesis that okay, the new treatment that I've made is better than the existing treatment. That was just to give you a clue on how the hypotheses are formulated, to say we can have this, it's not all about superiority, in other words, right tail test. It could be either way depending on the objective of our research question. So we've learned that the first step or stage is when we observe a difference. In other words, that's our research question. To prove this difference, we formulate an alternative hypothesis. Why do we formulate an alternative hypothesis? Instead of just because we haven't done our studies on the whole sample, let's say the whole population of people who take drug A and the whole population of people who take drug B, we cannot, if we had done that, there wouldn't have been any need for hypothesis testing. But because we carried out our studies on sample, we presume that even if this hypothesis is true, there would be some margin of error due to sampling fluctuation, in a sense that we randomly selected people, like we randomly, what should I say, include the people that we included in our study were randomly selected from a larger population into group A, who will be taking treatment A, and then group B, who will be taking treatment B. So there's an error that, okay, if we have a possible difference, or even if we don't even see a difference, that might be due to a random sampling error. So for this matter, because of random sampling error, we have to formulate a null hypothesis. In other words, the difference or the opposite results of our research question. To say, okay, if we are able to prove the opposite of our research question, or let's say if we are able to prove that the opposite of our research question is invalid, in other words, if we are able to prove that there is actually a difference in the actual population between mean A and then mean B, then at that point our research question would be valid. In other words, our alternative hypothesis would be valid. So because of sampling error, we have to define our confidence level. If we are saying there is no differences between the mean hours of sleep of people or patients who take sample A and patients, in other words, the new treatment and sample B, it could have been vice versa. You could have said, okay, maybe the new treatment is B, and then, but I, in this case, have made the new treatment to be labeled A. So if we are saying that the treatment, the people in the actual population, the mean hours of sleep after taking treatment A is not different from the mean hours of sleep. In other words, it's less than or equal to the mean hours of sleep of people taking treatment B, or in other words, the standard treatment. Then at what risk are we saying this? If really this is true, then what it means that we are still at a we in case there is a possible difference, if really this is true, let's say based on the fact that we worked on samples to estimate this, then it means we still have a risk of error, in a sense that we what do we say, we did sampling, we didn't study the entire populations. So this error is the way we term as random sampling error, or alpha risk, or alpha error. So we've decided to say, okay, we are somewhere 95% sure, and that's our confidence level, that this is equal to this, but we are not 100% sure, simply because there is 0.505 probability, in other words 5% risk, that this will not be true. The null hypothesis will not be true. In other words, this will not be equal to this. The mean of A will not be equal to the mean of B due to sampling error. So in other words, the alpha risk or the alpha error is actually in support of the alternative hypothesis. That's to say, if our confidence level is 95%, we are 95% sure that there is no difference, then due to sampling error, we cannot be 100% sure. So we still have a doubt of 5%, and that 5% is actually against what? The null hypothesis, to say there is no difference because there is a difference. There is a difference, and then the probability of this difference would be due to sampling error if really it doesn't exist any differences between A and B in the actual population. So let's move ahead. Now, we also have what we call the beta error. Why do we have beta error? In a sense that even with our research question, against our research question, in other words, on the alternative hypothesis, we still have some risk of error. So what that's to say, even if the alternative hypothesis is also true, there's still some risk of error due to a random sampling. Just as we are saying there's no difference, there is a risk of error, and that is 5% due to random sampling. If we are saying there is the difference, there's still a risk of error that this difference that we are observing might be due to random sampling. In other words, there's actually no difference. So this risk beta or beta risk or beta error is actually also in support of what? The null hypothesis. So this is how it works. But now the question that you ask is, why have we chosen beta risk to be greater than what? The alpha risk. This simply because we are working on a sample. So since we are working on a sample, we presume that's why we first of all have to validate the null hypothesis. We only come to the alternative hypothesis if the null hypothesis is proven to be false. So we've increased the risk of error, the risk of sample error to 0.2, in other words 20% against the alternative hypothesis instead of 0.05 as in the null hypothesis, simply because we usually presume that since we are working on a sample, there will always be a high risk of error due to what? Random sampling. So even if we observe a difference, then that difference, there's a higher risk of this difference being due to what? Random sampling error. So because of this, we increase, instead of 5%, we take beta risk to be 20% rather. And now, what it means is that if we are saying, if truly in the real population, there is a difference between the mean hours of patients who take treatment A, the mean hours of sleep of patients who take treatment B, if really this exists, and we are saying that at a risk of beta, that's to say at a risk of 20%, we are saying this because we are 20% uncertain that this really exists. In other words, if this really exists, our confidence level, this is also another confidence level, but I'll explain why we call it power of test. Our confidence level that there is a difference between the mean hours of sleep of patients who are taking treatment A and the mean hours of sleep for patients who are taking treatment B. Our confidence level would be, let's say, 80%. So what it means is that we are 20% uncertain due to random sampling error, and this 20% is actually for the null hypothesis but against the alternative hypothesis. So if the beta is against the null hypothesis, the alternative hypothesis, but in support of the null hypothesis, then what it means is that for us to actually be able to prove that there is a difference, then it will be 1 minus what? The probability of the alternative hypothesis not being true. The probability of the alternative hypothesis not being true is what we name as beta risk, in other words, due to sampling error. Now, if we know this to be 0.02, then the probability of the alternative hypothesis being true would be what? 1 minus the probability of it not being true. And that is what we term as the power of our test. In other words, the power of our test is the capacity of the test to prove that there is a difference between the population results, 2 or more population results, in other words, or sometimes a sample result compared to a population result, if really this difference exists. So what we are trying to say is that if really the mean hours of sleep of patients who take the new treatment is greater than the mean hours of sleep of patients who take treatment, the standard treatment or placebo, then if really this exists in the real population, then the capacity of our test to prove this will be what? The probability, the total probability, which is 1, minus what? The probability of this not being true, which is beta. So power of our test is the capacity of our statistical test or our study to actually prove that there is a difference if really the difference exists. So we are done with the second stage or the second step of our hypothesis testing procedure. We have formulated our hypothesis, and then we've also fixed our confidence level and then our risk of sample errors. In other words, the random risk, that's beta and alpha, we've done that. But you have to note that alpha and then beta are not always just fixed at 0.05. It depends on the test conditions. They could increase and they could decrease. For example, with a larger sample size, that's to say when we have a very large population sample size, what it means is that there's a high probability that the sample size would be representative enough of, in other words, its distribution will be almost like that of the population. So we are likely to get results that will be more similar to the population results. So in that sense, the risk of alpha would what? Decrease. That's to say sampling error against the null hypothesis would be small, and at the same time sampling error against the alternative hypothesis would be small because we had a very large sample size. Sample error, in other words random error against the null hypothesis, which is alpha, would decrease, and at the same time sample error against the alternative hypothesis would also decrease. Now let's take it again. I think this is clear. So that's just to tell you that okay, alpha and then beta are always fixed at 0.05. It depends on the sample size and then other factors. The next step is to what? After knowing, let's say, alpha, what's actually the purpose of alpha? Alpha will help us get the critical value. In other words, the theoretical statistical value of our sample distribution, which is T alpha. Now, the fourth step is what? To now calculate the observed statistical value. This is still a value for our sample, but this is what? Hypothetical. In other words, this is theoretical. This is based on the fact that statisticians study several populations with respect to maybe calculating mean, and they came out with the idea that, okay, with a given sample size n, which will give us a number of degrees of freedom, the distribution of the population could be labeled by a particular statistical value. In other words, this statistical value is simply a function of the change or the differences that we are trying to study in the population, considering the sample size, the variance, in other words, standard deviation, and many other parameters. With a given sample size, the distribution of the population, if we are trying to infer, it will respect a particular function. Now, this is just a function of the change that we are trying to observe in the population theoretically. So this, but if we are trying to find the actual, in other words, the observed statistic value of our sample, then at the end of the day, we would label that one as an observed statistical value. Then at the end of the day, we compare the results of this observed statistical value to the theoretical, in other words, the norm. That's to say, we will get to see how we conclude. But that's to say, if at the end of the day, this observed statistical value is greater than the theoretical statistical value, in other words, the norm that has been fixed by the statisticians after studying several populations, then if the observed statistic is greater than the theoretical statistic, then at that point, we would say that there is a significant difference between what? The two treatments, for example, between the two populations that we are comparing. In other words, treatment A would be what? Actually superior than treatment B, or it could be the other way around. But in either case, there would be a difference. That's what is, because it's that difference that has what accounted for the increment of the observed statistic compared to the what? The theoretical statistic. Remember I said the statistical value is simply a function of what? The difference. It's a direct relation. In other words, the statistical value is proportional to the difference. So when the difference is greater, or is greater, like between A and B, then what it means is that we're going to have a larger statistical value, and that larger statistical value would be what? Greater than the norm. And at that point, what it means is that in actual sense, this difference wouldn't be due to sample error, but it would be due to, this is the value that we are supposed to get due to sample error. That's why we wrote alpha. That's the risk of error, sample error. But if this is greater than this, then what it means is that there is something that has accounted for it, either than sample error. So it's no more risk alpha. In this case, risk alpha, the probability risk alpha will be what? Less than the p-value, which is the random sample error for what? The observed statistic. And then we would say there is actually a difference. In other words, the alternative hypothesis will be true. Without wasting my time, we will see how we conclude at the end of the day, but I'm trying to explain at the same time. So the fourth stage would be calculating the observed statistics. Now, what's the purpose of calculating the observed statistics? With this, we would be able, with some degrees of freedom based on the sample size, we would be able to get what? Our p-value. Now, what it means is that the p-value plays the same role just as what? Alpha. P-value is also the same as alpha, but just that p-value is actually, that's why I said we could say p-value is the same as observed alpha. So this is theoretical alpha, this observed alpha, in other words, the p-value. This one is the random sampling error against what? The observed statistic. Whereas alpha is the random sampling error against the theoretical statistics. That's to say, alpha is trying to say if there is no difference between A and B in the actual population, or if there is no actual difference between A and B in the actual population, then I think I've already explained this. I don't need to repeat myself. But what we are trying to say is that alpha is the same as p-value, but p-value is alpha is the same as p-value, but actually alpha is what based on the observed statistic, in other words, the theoretical model, whereas p-value is based on our observed model. So we are comparing this to this. You realize that we can conclude based on if observed t is greater than alpha, t alpha, then we could conclude. If it's less than whatever it is, we can conclude based on these two, or we could also conclude based on what the p-value. So when we compare our observed model to the theoretical model, so this also our observed alpha. Now what happens is that if observed alpha, in other words, if the p-value, in other words, the probability that the differences that we've observed would be due to random sampling error, or in other words, the probability that if really the null hypothesis is true, that's to say, if the mean hours of sleep of people who are taking treatment A is equal to the mean hours of sleep of people who are taking treatment B, if this is actually true, then this observed statistical value that we've calculated on our sample distribution, if this is actually true, then we would be, let's say, 1 minus 1 minus p confident that this difference will be observed. This will be 1 minus p confident that like the null hypothesis will be true, and then we would be we would have at a risk of p that the opposite would happen due to sampling error. So to conclude, what do? We now compare the probability, the observed probability, with the theoretical probability. So remember, this alpha is the theoretical probability against the null hypothesis. P-value is the observed probability. Alpha is the theoretical probability against the null hypothesis. P-value is the observed. Let me take it again. Alpha is the theoretical probability against the null hypothesis in support of the alternative hypothesis. P-value is the observed probability against the null hypothesis in support of the alternative hypothesis too. So we are now trying to compare these two. This theoretical, in other words, this is the norm. This is the observed. This is our actual probability. So what it means that both are representing a random sample error to say they are all against null hypothesis. So right now, but this is the norm. In the case where the p-value is less than alpha, then what it means is that we have lesser probability that if really what should I say, if really, let me take it again, if p-value is less than alpha, then what it means is that we have a lesser probability that the observed results would be due to sampling error. So if there is a lesser probability that the observed result will be due to sampling error, then simply we could conclude that the results is significant, is statistically significant. In other words, the differences that we observe on the alternative hypothesis is actually not due to sampling error, but it really exists in the real population if we are making our inferences. But if p-value is actually greater than the norm, that what we are trying to say is that there is even a higher probability that the results that we've obtained, in other words, the difference that we have obtained on our sample, or on the, what should I say, on the two populations, if p-value is greater than this, then what it means that there's a higher probability that this difference would be due to a random sampling error. And if there's a higher probability of this being due to random sampling error, then it means the null hypothesis is true. What it means that in actual sense there's no difference, but the little difference that we are observing is actually due to what? Random sampling error. That's why the p-value is greater than what? The theoretical risk, alpha risk, or in other words, the theoretical random sampling error. So this is how it is. That was just to explain so that you would have a better understanding of why we say whenever p-value, for instance, is greater than alpha, then we don't have to reject the null hypothesis. But now, remember that not rejecting the null hypothesis does not mean we have accepted a null hypothesis. If we do not reject the null hypothesis, it could be that there is actually a difference. Actually, it could be that the alternative hypothesis is true, but we don't have, our sample size was not maybe large enough to prove this difference. So when we do not reject the null hypothesis, in other words, when p-value, which is the observed random sample error, is greater than the theoretical, in other words, the norm of the random sampling error against the null hypothesis, we don't have to conclude by saying, okay, the null hypothesis is true, but we say we cannot confirm, in other words, we cannot affirm that there's actually a difference. But it doesn't mean there's no difference. Probably it's due to the fact that our sample size was not large enough. In other words, the power of our test was not that sufficient. On the other way around, when p-value is less than alpha, then we can reject the null hypothesis. When p-value is less than alpha, as I said, what it means is that the probability that the difference that we are observing, the probability that it will be due to, let's say, random sampling error, that's to say the difference does not actually exist, it's actually due to random sampling error. If that probability is less than the predefined probability considering our sample size, according to those statisticians who did their study and came up with the distribution of the for example, the t-statistic, then what it means is that there is a lesser probability that the observed difference would be due to what? Random sampling error. So if the probability, if there's a lesser probability that the observed difference will be due to a random sampling error, then what it means is that there is something that actually accounts for this difference either than the random sampling error. That's to say treatment A is actually better than treatment B, and this difference that we are observing is not due to the fact the sample fluctuation or the fact that we randomly selected people, let's say, from the larger populations, and then due to this random selection, probably we took fewer people who respond well to treatment B. So at the end of the day, we realized that maybe treatment A was doing better than treatment B. It's not the case. What it means is that treatment A is actually better than treatment B. That's why the random sampling error of the observed statistic is less than what? The theoretical statistic. To back all that I've said, especially for those who like reading, I've decided to put down some definitions. So assuming that all the test conditions were met, in this case it was t-test. That's to say there are different kinds of tests. It could be when we are comparing percentages, we could use or proportions, we could use key-2 test, we have Fisher test, we have what do you call it, z-test, then we have t-test, we have there are so many kinds of statistical tests. So but I decided to use mean just to explain the procedure. It doesn't mean it's always all about comparing two or more population means or a sample mean to a population mean. It could be a sample percentage to a population percentage, a sample variance or standard deviation to a population standard deviation. But I just use mean to explain the procedure, so don't limit yourself. So to define alpha risk, in other words, the random sampling error or the first species error in hypothesis testing, assuming that the test conditions are met. If truly the null hypothesis is true, in other words, if truly, in our case, the average hours of sleep of patients who take the new treatment, which is treatment A, is actually less than or equal to the actual, what should I say, the average hours of people who take, of sleep of people who take treatment B, then what it means is that alpha, the probability or the risk of getting the opposite results, the probability that the null hypothesis will not be true, as alpha is actually in support of the alternative hypothesis. In other words, the mean hours of sleep of patients who take treatment A being greater than what the mean hours of sleep of people who take treatment B will only be due to random sampling error. So we are, in other words, we are 95% sure, that's our confidence level, that if truly the null hypothesis is true, in other words, there's no actual difference between the populations from our sample studies, if truly this exists. But because for the fact that we just conducted our studies on the sample, then the risk of error of the alternative hypothesis being true would be very less. It will be minute. It will be only 5%, and that 5% will be what attributed to the fact that we randomly selected our population, our samples, and that risk of error is actually due to a random sampling error. Now, beta, as I said, is also another random sampling error against what the alternative hypothesis, but in support of the null hypothesis. That's to say, if truly the alternative hypothesis is true, in other words, treatment A is better than treatment B, then the probability or risk of getting the opposite results, in other words, of of having no difference between the true treatments, in other words, the true treatment having the same efficacy, will only be due to the random sampling error. And we fix this as 20%, but I said it depends on the conditions. Alpha and beta are always fixed at 20%. It depends on the test conditions. If we have large number sample size, we could decrease alpha. In the case where we have different judgment criteria, like combining them, what it means is that in order not to to increase the risk of concluding that, let's say, there's no difference, then we would have to, because when we have different, let's say, a judgment criterion that is not precise, because probably it wasn't just about the mean hours of sleep, it was, let's say, there were other things in addition, maybe the mean hours of sleep and then maybe something else, in order not to to exaggerate the probability that our results will be due to random sample error, then we would have to decrease the alpha. So that's just to tell you that it's not always fixed. Now, then what it means is that beta, which is usually fixed at 20% conventionally, then the probability that the alternative hypothesis is true would be what? 1 minus the probability that the alternative hypothesis will not be true. And that's 80%. In other words, 80% conventionally is always what? The power, our test power. 80% is the ability of our test to actually prove that there is a difference between the two populations. this represents, as I said, the power of the statistical tests. Now, the last, not the last, but not even the last, we still have something to look at, I guess. But now, just as I said, 1 minus beta is what we call the power of our test, or the test power. Now, the power of the test is defined as the capacity of the test to prove that there is a difference. In other words, a statistically significant difference between test results if truly the difference exists in the actual population. And then p-value is just the same as alpha, but p-value is to me is the observed alpha. Since we conducted our studies on a sample, this p-value actually represents the random sample error of our sample results. Let's say if we are to infer the population result, that's what p-value actually stands for. But alpha stands for the same thing, but in a theoretical context. Statisticians came out and fixed alpha to be 0.05. So now we compare our p-value to what alpha in order to make our conclusions. So p-value, to define it, if truly the null hypothesis is true, then p is the probability. In other words, p-value is the probability of obtaining test results as least as extreme as the actually observed results. In other words, p-value is the probability of obtaining what? Let me use the pointer, please. P-value is the probability of obtaining this test statistical value or more if the null hypothesis is what? Is true. In other words, if the alternative hypothesis, the null hypothesis is true, that's if the mean the mean hours of sleep of treatment A, for instance, is less than or equal to the mean hours of sleep of treatment B, then P is the probability of obtaining the statistical value to be greater than or equal to what? The value that we observed after the calculation. That's TO. Do not get it twisted. Simply, p-value is the probability that the results that this based on the sample observation, p-value is the probability that our test results will be due to a random sampling error. That's why when p-value is greater than the predefined alpha, which is also the probability that the theoretical probability that the sample would only differ from the the population results by the fact that we did sampling, in other words, due to random sampling error. This is the theoretical value or probability value, which is alpha. P-value is the observed probability value. So what happens is that when p-value is less than alpha, then what it means that there's a lesser probability that the observed difference will be due to random sampling error. Then we conclude that really the differences exist. In other words, the difference exists between what? Treatment A and treatment B. On the other hand, if treatment p-value is greater than alpha, then what it means that there is a higher probability that the results, this difference that we've obtained between the mean hours of sleep of patients who take treatment A, the mean hours of sleep of patients who take treatment B, would be what? Due to random sampling error. In other words, what it means is that there's no actually difference, but the difference that we are observing is due to what? Random sampling. The fact that we have haphazardly selected or constituted our samples. Thanks for watching, and please remember to subscribe. Bye.